to inflammation. Please, Anastasia, you can begin your presentation.
Thank you very much for the opportunity to present here today. And yes, I would like to tell about some our models which we construct and investigate to study the infection propagation in tissue with respect to inflammation. These models are done and these analyses are done with my colleagues. They are Professor Volpert Vitaly Isakovich, Latifa Mayu, and Miriam Buzari. Here is outline of my today's talk. I will start from a bit of physiology background, then I will talk about the models. I would like to talk today about three our models. They take into account different aspects of inflammation, and each next model is somehow the generalization of the previous one and about results which we obtain in these models. The first part is about physiology background. We consider the respiratory virus infection, which enters into the organism and infects epithelial cells of upper respiratory tracts. When virus enters into the target cell, it unfolds its genetic material and the cell becomes infected. Infected cells start to produce new viral particles and at the same time inflammatory cytokines. Inflammatory cytokines are some chemical mediators which there are different kinds of these cytokines, and they have different influence on different processes. Cells use them to interact with each other. They help to orchestrate the immune response, and also they alter the I think we can say like this, the behavior of cells nearby. More precisely, when inflammatory cytokine enters to the cell nearby, it becomes also inflamed, and the inflamed cell produce new inflammatory cytokines from the one hand, and from the other hand, it can die faster because of different mechanisms of cell death. In this work, we consider the following aspects of pro-inflammatory cytokines. We consider that they are produced by infected cells. They can be produced by, they are produced by circulating macrophages and by resident macrophages. And we consider the following actions of them. They lead to recruiting of the pro-inflammatory macrophages and stimulate the immune response. And when a cell becomes infected cell becomes inflated, it dies faster because of apoptosis, necroptosis, or pyroptosis. As a result, the effect of pro-inflammatory cytokines are that the number of amount of the infected cells reduces. These main aspects are presented on the scheme, and all the models are, which I will talk about, are based on the scheme, but we not for all models take into account all these processes. Here we have infected and uninfected and infected cells. When a virus penetrates into the uninfected cell, it becomes infected, and at the same time it becomes inflamed. So infected cell in our models produce new viral particles and pro-inflammatory cytokines. Pro-inflammatory cytokines influence the two types of macrophages. We have here resident macrophages. These are cells, macrophages, which are placed in the tissue. They always placed in the area of in this area, and they also lead to recruiting of the circulating macrophages. They come from the blood flow. So in tissue we have resident macrophages, and in blood we have circulating macrophages, and cytokines, pro-inflammatory cytokines, lead to activation of the resident macrophages and recruiting and also activation of the circulating macrophages. It happens that resident macrophages, I suppose, react faster to the infection because they're closer to the infection region. Macrophages phagocyte the infected cells and present the virus parts on the membrane surface, and it part of the immune response, but we will not consider this part in our model. We consider only the phagocyte aspects, and these arrows show that macrophages phagocyte infected cells. And cytokines, there are different types of pro-inflammatory cytokines. In particular, there are one of inflammatory cytokine is TNF-alpha, which lead to more fast death of the infected cells. So infected cells can infected cells can die as a result of virus infection, and because of reasons some different from viral infection, and one of this reason is because the influence of pro-inflammatory cytokine, something like this. So in the first model we include only these three parts, and this is start model, and I will remind all main results which we obtain in this model. This model includes three quantities. It is uninfected cells, infected cells, and virus. And they interact like this. We have amount of uninfected cells. When virus penetrates into the uninfected cells, it becomes infected. Because of this, we have this term in the second equation. The second equation describes dynamics of the infected cell. It the cell becomes infected because of infection, virus penetration into the uninfected cells, and it dies. And the third equation is for virus. We consider the virus production by infected cells with some time delay, and there is virus degradation, and we also take into account the virus diffusion or its random motion in the extracellular space. This model is of reaction diffusion type, and in this model we can obtain and will find the following characteristics. This virus replication number, total viral load, and speed of the wave propagation. Virus replication number, it is a number, it is some relation of coefficients of the model, which shows if the infection will propagate in this model. Total viral load, under the total viral load, we understand the space integral of the virus concentration variable showing the virus concentration, and it shows the full amount of virus particle in considered tissue or cell culture. And for the respiratory virus infection, it corresponds to the virus infectivity, how easy one infected individual infect others. And the third characteristic is speed of the wave propagation. This system can have the solution which propagates like a reaction diffusion wave, and the speed of the wave propagation corresponds to the virus virulence, or which corresponds in turn to the severity of the disease. The solution of such system, the wave solution of such system, can have the form like this. This is sorry that this is the solution for different system, but for this one it will be the same without this red line. So we have some structure of this kind, and it propagates in time from left to right, preserving its form. So the solution of such type we will call wave equation, and for this wave solution we will determine the viral load and the speed of the wave propagation. I will remind the main results of this model. In this model without diffusion, so in the reaction part of this model, we can find the stationary points. In the reaction model, we can find the stationary points, and if we fix the initial condition, we take the initial condition, which is the amount of, which equals to the amount of uninfected cells on the start of the infection, we can obtain stationary point, and it will be stable when the following condition will be hold. And this ratio which we obtain in this analysis, we call it virus replication number. It shows whether the infection will propagate. If the virus replication number is less than 1, that it means that the stationary point of this kind will be stable. And this point, it means that we have the initial number of uninfected cells. I have there should be 2 zeros, and 0 for infected cells and 0 for virus concentrations. So this point is corresponds to the healthy state, the state when there is no infection. And when RV, virus replication number, is less than 1, then this point is stable. It means that we have no wave structure like this in this case. The wave structure we can obtain in the case with diffusion when virus replication number is more than 1. In this case, we understand this case that it corresponds to the infection propagation. In the system with diffusion, we can estimate the minimal wave speed, the speed with which this wave structure will propagate from left to right. And we can do it with linearization method and obtain the following equation for C, which is the wave speed. We have some function in the right-hand side, and this function is presented on the picture. The denominator has the positive root if and only if virus replication number greater than 1. So when the virus replication number greater than 1, from the one hand, the healthy point becomes unstable, and from the other hand, we have positive root in the denominator of the function f at mu, and because of this, we will have the minimum of the function and can obtain the wave speed of this minimax by this minimax representation. Next, in the system with the wave, we can, the wave speed corresponds to the severity of the disease. We have some formula and we'll compare other models with this result for this case when there is no inflammation in the system. The next characteristic is the viral load, and for the viral load, we can, in the original system with diffusion, we can go to the wave variable. Unfortunately, I didn't write it here. It's a variable C, which is x minus ct, where c is wave speed of the wave propagation. To estimate the viral load, we suppose that we know the speed of the wave propagation, and doing some calculations, we can obtain the this equation for the speed of the wave or for the total viral load, where omega is the solution of the equation 8, where we also have the virus replication number. And this equation has the solution in the interval 0, 1 only if virus replication number is greater than 1. We consider only the solutions in 0, 1 because of the biological sense of the variable omega. It is a ratio of the amount of uninfected cells on the end of the infection to the amount of the uninfected cells on the start of the infection, at the beginning of the infection. In the next model, we also consider cytokines. So the scheme of interaction now is like one presented on the picture. We have uninfected cells, we have uninfected cells, and we have virus, and we have pro-inflammatory cytokines. We consider that pro-inflammatory cytokines production is depends on the quantity of infected cells, and cytokines decrease the amount of the infected cells. Other flowchart are the same, and the model is like this. We have new terms in the second equation and in the new fourth equation. In the second equation, this term shows corresponds to this arrow, this red arrow, and the last equation is the dynamics of the pro-inflammatory cytokines. The production of pro-inflammatory cytokines is proportional to the amount of infected cells in the infection region, amount of all infected cells in the infection region. And this term corresponds to this one, so this is decreasing of the cytokines because of their penetration into the infected cells. And the last term can be interpreted as degradation or clearance of cytokines from the infected region. The last equation is the ordinary differential equation because we consider here that cytokines depends only on time and they do not depend on space variable because we suppose that the concentration of cytokines very fast become equal in each space point. It can be the reason of it can be, for example, blood flow, because blood exchange and blood flow is much faster than this rate of infection propagation. So we can consider here that concentration of cytokines is the same at every space point, and thus the function of concentration of cytokines is function of the time only. And because of this, here we have integrals which represent the full amount of infected cells in time t. So these integrals are functions of time, and they have the following form. It's integrals on the it's integral from the concentration of infected cells on space variable. We have here different designation for the infected cells, but it is the same equation as we have before, except for this blue term. And when we analyze analytically this system, we consider these integrals from on the whole real axis. In numerical simulation, it will be considered on the bounded interval from 0 to L or something like this. But in analytical, we have integral on the whole real axis. In this system, we can repeat the same analysis which we did before and investigate first the system without diffusion. In the system, we can consider two cases. And the first case is when we have no clearance or degradation of cytokines. It can be like this, for example, on early stages of the infection when there is no clearance, or maybe there are some different nature. But if it is like this, we have stationary point of such form, and virus replication number is given by this formula. It changes from the previous in this one term in the denominator, which depends on the parameters of production of cell death, of infected cell death due to inflammation, and here it multiplies to the initial concentration of inflammatory cytokines. If there is no cytokine clearance and degradation, we have the stationary point of the same kind as before. Here we have non-zero concentration of uninfected cells, and all others concentration are zeros. And for this case, we obtain virus replication number, which is exactly the same as we have in the model without pro-inflammatory cytokines. And the following estimation is true for the virus replication number in the case without clearance of cytokines and for the case with clearance. And for the case with clearance, we can conclude that introducing in the model the inflammatory cytokines does not change the condition of infection progression. So we have the same virus replication number, and as before, if this virus replication number less than 1, we have no infection progression, and if it is greater than 1, we have infection progression. So inflammation does not influence this in any way for the case with no clearance. Next, we analyze the system with diffusion. Also, there are two cases. The first case is when we have no clearance without degradation, and in this case, we can obtain the equation for final concentration of uninfected cells. It is also the same as in previous model, except for these blue parts. Here we obtain new parameter, which is joint parameter of all initial parameters of the model, which determine the behavior of cytokines, the influence of cytokines in the model. So K3 is infection infected cell death because of inflammatory cytokines. Cas6, as I remember, it is yes production of cytokines, and Cas7 is the it shows how much cytokines should penetrate to the infected cells. So it like Ca3, but in different equation. This equation also has the solution in the interval from 0 to 1 if and only if RV2 is greater than 1, and here RV2 depends on alpha, which is shows the effect of inflammation, and all the inflammation parameters are included in this parameter alpha, and thus we call this parameter alpha the inflammation-induced death on infected cells. And because this inflammation-induced death, it changes for us the virus replication number. Total viral load is the same as before, and the wave speed is the same as before, but here we also have this parameter alpha. It increases the cell death. Sigma 1 is the infected cell death in the first model, and alpha the infected cell death because of inflammation. So here we have increased death of infected cells. I show a little bit later the dependence, the function plot of the dependence of the wave speed and total viral load on this parameter alpha, which is inflammation-induced death of infected cells. In the system with diffusion, now we consider the case with degradation of inflammatory cytokines. So we suppose that sigma 4 is not 0, and in this case we have the following equation for the final concentration of uninfected cells. It also differs from the previous one by these blue parts. We have one more multiplier here and one more multiplier here. For the parameters, this is like before. We get new parameter, which is beta, and beta, we call it the effective clearance of cytokines because it is ratio of parameter showing the clearance of cytokines, the rate of clearance of cytokines, divided by some other parameters. So it's effective clearance. And for sigma 4 is not 0, we have this parameter beta also is not 0, and because of it, these parameters Q and R also not 0. If they are 0, we get previous case. This equation gives us the previous equation. The equation for the total viral load is the same, but the same formula, but now the omega is the solution of different equations, so it also changes. And in the wave, for the wave speed, we also have a bit different equation. And also, if beta is 0, we can simplify it and get the previous result. J from omega is the integral on the whole real axis of the infected cell. So this is the total amount of the infected cell, but it can be calculated with the total viral load, with the total concentration of viral particles. So the next, we consider the dependence of the viral load and wave speed on these two inflammatory parameters. At the end, we obtain two inflammatory parameters. This is parameter alpha, which is inflammation-induced infected cell death rate, and the second parameter is parameter beta, which is the effective clearance of the cytokines. The first figure, figure A, is dependence of wave speed and viral load on the parameter alpha when parameter beta is 0. So this is the case for no cytokine clearance. And for this case, this line is for the total viral load and this line for the wave speed. And such form of the line for the wave speed can be, we can explain it by the form of the virus replication number. So when parameter alpha is more, we just obtain then that virus replication number is less than 1. Increasing parameter alpha leads to decreasing of the virus replication number. So in this parts, virus replication number becomes less than 1, so we have no wave solution in this case. Figure B is also the dependence of wave speed and total viral load on parameter A, which is the inflammation-induced infected cell death rate, but for this time for not zero clearance of cytokines. So if there is clearance of cytokines, some fixed but not zero, we can see that parameter alpha reduces both wave speed and total viral load, which means it reduces both disease severity and disease in virus infectivity of the considered infection. Figure C, this is the dependence on the parameter beta, also the dependence of the wave speed and total viral load on the parameter beta, now when alpha is equals to 0. So we have production of inflammatory cytokines, but these cytokines do not lead to the infected cell death rate, to the infected cell death. If it is like this, when alpha is 0, we obtain that the wave speed and the total viral load do not depend on the rate of clearance of these cytokines. And the last figure is the same as previous, but for alpha not 0, some fixed value but not 0. And in this case, we can see that increased clearance or degradation of pro-inflammatory cytokines leads to increase of the wave speed and of the total viral load, that is of the virus of the disease severity and virus infectivity. So the results of the investigation of this model are as follows. The inflammation-induced death of infected cells do not determine whether the infection will develop. This is true for the case when there is clearance of cytokines, and I can correct this a bit. When we have no clearance of cytokines, it influences the virus replication number, and as a result, it will determine whether the infection will develop. But in the case without clearance, with clearance, it does not influence on this. Influences this. The next conclusion is that inflammation-induced death of infected cells decreases both severity and infectivity of the disease in both cases with and without cytokine clearance and degradation. This is these two pictures. The next one, that the cytokine clearance increases the severity and infectivity of the disease when there is inflammation-induced infected cell death, and it has nothing influence if we have alpha 0. And the last conclusion, I would like to explain it on the previous slide. Here we have some maximum for functions or which correspond to the wave speed and to the total viral load. And here we also can notice that both function tends to some limits, and this limit we can calculate. We did it both for both analytically and numerically, and obtain that value which are the limits in all these cases. It is the values for wave speed and the total viral load in the previous model of 3 equations without inflammation. So when there is inflammation and this is their values, so picture C corresponds to the it has the same values as in the system without inflammation. So when we there is a mechanism of inflammation, even this symbol which presented in this model, the virus severity, the disease severity and the virus infectivity both less than in the case when there is no inflammation. So they are bounded from above. Here, just to comment something on what values of parameters alpha and beta did we take. We take different values of parameters, and we even check more values than presented here. There is surface where we have alpha, parameter beta, and total viral load, and also parameter alpha, parameter beta, and no, this is wave speed, and this is total viral load. And we can see that in all fixed value of alpha and beta, the qualitative characteristics of the lines will be the same as presented here. And for all these values of parameters, the upper boundary is the values of wave speed and total viral load in the system of 3 equations. The next model and the final model, which I would like to tell about today, it is our recent model, which includes the influence of resident macrophages. Here we have following interactions. We have in uninfected cells, when virus penetrates into it, it becomes infected, and infected cells, as before, produces new viral particles and pro-inflammatory cytokines. And I don't know why I didn't show this line. The pro-inflammatory cytokines, they, as before, inhibit, decrease the quantity of infected cells, and also they in this model they only decrease the quantity of infected cells. And the virus, virus particles, they do not only penetrate into uninfected cells, but also they activate resident macrophages. So we have resident macrophages which are placed somewhere in the tissue, and when the virus interacts with this macrophage become activated, and activated resident macrophage produce new cytokines. In the start of the infection, there are fixed amount of resident macrophages in the infection region, and we do not consider the influx of circulating macrophages now in this model. And in the early stages of the infection, we suppose that macrophages do not proliferate. So the model system the equations of this model are as follows. We have the same equations as before for uninfected cells and infected cells. We have different notation for uninfected and infected here, but it is the same equations. They are exactly the same as before. We have new equation for M, which is the concentration of resident macrophages which are not activated yet, and we have new concentration for activated macrophages. Resident macrophages activated by interaction with virus, and as a result, they become activated macrophages, and activated macrophages can lose their activity or die. So we include this term in this model. And we also consider that, take into account that now pro-inflammatory cytokines are not produced only by the infected cells, but also by the activated macrophages. So we have increased production of infected cells because of their production by activated macrophages, and this term shows it. As before, the J from some concentration are the integrals, are the space integrals, and as a result, we obtain the time functions, and the explanation for this is the same as before. We suppose that cytokines quite fast distribute in the infected region. For this model, we also can investigate the system without diffusion. It happens like nothing at all changes for the system without diffusion. We have the stationary points. There is for initial concentration of macrophages, but it does not influence the virus replication number in the case with cytokine clearance, and also it does not influence in the case without the cytokine clearance. Both these values the same as we have in the model with inflammation without resident macrophages. In the case with degradation of inflammatory cytokines, we obtain the following equation for the final concentration of uninfected cells. It's also a transcendental equation, and we were able to show that this equation has solution if and only if virus replication number RV greater than 1. It's interesting that this RV is the same as we have in the very first system. So new aspects, not the inflammatory cytokines nor the resident macrophages, does not influence the whether the infection will be or not. So will it propagate or not? Here, this equation changes from the previous with this blue part. If it is 0, then we obtain the previous model and previous equation. Here are all the same parameters. We have parameter alpha and beta. Alpha is inflammation-induced infected cell death, and beta is effective clearance of inflammatory cytokines. Next, we obtain the same equation for the total viral load, but as before, we have different solution for omega, because omega now is the exact solution of this equation, changes a bit, and we have changes in the representation of the wave speed. So this is a function which we find the minimum in the right-hand side, and we obtain new terms in this part with new coefficient, which can be interpreted as infected cell death, which is happen because of cytokines which were produced by by tissue-resident macrophages. So I called here the tissue-resident macrophages induced death of infected cells. We have one additional term. It's quite complicated to analyze these two formulas. They relate to each other in the equation for the wave speed. This is the right-hand side of the equation for the wave speed. We have the concentrations of GF and GN, which depend on the total viral load. And in the equation for viral load, we have coefficients Q, coefficient Q, coefficient R, which depend on the wave speed. So it's quite hard to investigate these two equations, but we can investigate the simpler case, which we obtain when we consider that there is no clearance of inflammatory cytokines or no degradation of inflammatory cytokines. In this case, we have simple equation. It's like this, and it changes from the equation which were obtained in the case without tissue-resident macrophages by this term. And it can be shown that this equation has a solution in interval 0-1 when RV2 is greater than 1. RV2 now this one, which depends on the inflammation-induced infected cell death. I was not able yet to show that there is no solution in the case when RV less than 1, but we consider RV greater than 1. And the function for the wave speed, we can rewrite it in this form, and in this form we obtain these new terms, gamma R. R, it is the ratio of these two concentrations, and it can be shown that this ratio is constant now. So this is infected, inflammation-induced infected cell death rate, which increased by this constant linearly. And for us to be able to obtain the minimal wave speed, we should have the positive root in the denominator. And this function will have the positive root in the denominator when the following equation, the following inequality is satisfied. Here are with the virus replication number. Also, it is the same as in the very first model. And we obtain here a new number, which is number P, which is some ratio of inflammation parameters and other parameters, and all inflammation parameters which are included in the model. And here I call it the immunity effectiveness number because it is some joint parameter which characterizes the effectiveness of the immune response, in our case, the inflammation part of the immune response. We can, so now for the infection progress, we should have that virus replication number should not only exceed 1, but it should exceed 1 plus some positive value plus some different number which shows the effectiveness of the immune response. Here are the plots of this dependence. In the left, we see this function f and its dependence on the this value p. So we have different values p, and for the third one, we obtain the case when this inequality is not whole anymore. it's like this. So at some point, we do not have this minimal point of minimum, and we interpret this case as we do not have wave solution in this case. For the wave speed, it decreases when we increase coefficient K1. It corresponds to the increasing of the infected cell death, both due to the cytokine influence, which we call this parameter alpha, and also due to tissue-resident macrophages influence, also through cytokines, which we call gamma. And this curve has the same form, and I think it should be interpreted the same way which we have in the previous model with inflammatory cytokines and without tissue-resident macrophages. The same also true for total viral load, so increase of the K1, which leads to increase of the inflammation parameters alpha and gamma, leads to decrease of the total viral load, which corresponds to the virus infectivity. Here are the results of the last model and the results of the previous model I showed it before. In this model with resident macrophages, we obtained that clearance do not determine whether the infection will develop. It's yes, it's in the case with clearance. So as it was before in the model without tissue-resident macrophages, but with inflammatory cytokines. Without the clearance, we influence of cytokines produced by tissue-resident macrophages decrease both the severity and infectivity of disease, and we can here obtain the immunity effectiveness number, which shows how strong the immune response is. And for existence of the minimal wave speed, which we interpret as existence of the wave solution, which means that for infection propagation, the following inequality should be satisfied, and whereas it means that for virus infection to develop in tissue, virus replication number should be greater than for the virus infection to develop in cell culture. So for the virus, it's easier for it to start the infection propagation in the cell culture than in the tissue because of the immune response, and we get some estimation of this rate of degree of this immune response. The next, we would like to continue the consideration of these processes and maybe take into account the circulating macrophages or maybe interaction with resident macrophages. I think we will talk about it later. And there are some references to the publications which were used in this talk, and thank you for attention.
Yes, thank you, Anastasia, for this presentation. We have some time for discussion. Please, if there are questions from the audience, you can ask. So to summarize all that, as you say, so what is the influence of inflammation on viral infection? So please, you told that, but I think it might be useful to repeat. So in all these models you consider, so your conclusion is that inflammation reduces viral load, and inflammation also decreases the way speed, which correlates with virus infectivity, right?
Yes.
Sorry, with virus virulence, sorry. So inflammation, in some sense, according to all these results, is as a part of the immune response, has a positive role reducing infectivity and virulence of viral infections. This is the main conclusion of all the studies.
Yes,
right?
We have such main conclusion.
All right, with this optimistic conclusion, let us consider now this scheme, what you showed in the beginning with these small squares and this, for example. Yes, so what we have here, so the cytokines, they kill infected cells, and this is why, in fact, we have this positive influence of inflammation, which as a part of the immune response acts to stop infection progression or infection propagation. On the other hand, we know also that in the immune response, there are not only pro-inflammatory cytokines, but also anti-inflammatory cytokines. In this work, we did not yet discuss this question, but we discussed it in other works, in particular with some where we study inflammation, the role in inflammatory diseases, but not in viral infection. So and what is the role of anti-inflammatory cytokines? They downregulate production of inflammatory cytokines. So a little bit strange, right? So these inflammatory cytokines, they have a positive role. They try to stop infection. On the other hand, anti-inflammatory cytokines try to stop inflammatory cytokines. Why it is like that? Why it looks like our organism plays against itself, right? So instead of helping stopping infection, what is done by inflammatory cytokines, it stops production of inflammatory cytokines. So in some sense, it promotes infection. So could you comment on that?
It's a very complicated question. One part of the answer is because I talked it before, but did not consider this part in my today's talk. We did not consider here the negative influence of pro-inflammatory cytokines. This negative influence can be, for example, that cytokines make uninfected cells also inflamed, and inflamed cells die faster than uninfected cells. So they can decrease the amount of uninfected cells, and it will not be beneficial for the, I suppose, for the viral infection as well. And I think it will be interesting to investigate this case. From other hand, second point of this answer is that pro-inflammatory cytokines are, many of them are pyrogens, which lead to rise the temperature in the body. So here we can come to the complex question of temperature and its influence, and it not for all systems of organism it has beneficial influence. So, or maybe to decrease the negative parts of the pro-inflammatory reaction, we should have the anti-inflammatory cytokines and part of this balance.
All right, so as you said, there is a complex balance between pro-inflammatory and anti-inflammatory cytokines, but not only cytokines, also macrophages, because you consider here this resident and circulating macrophages, but both of these types in your model, they act as pro-inflammatory macrophages.
Yes.
You know, of course, that, well, now I address not only to you, but also to our listeners, we know that both of them can be pro-inflammatory. They call it M1 type macrophages or classically activated macrophages, but also M2 type macrophages. They are called alternatively activated macrophages, and they are anti-inflammatory. So it's also an important part of the immune response because there is this complex balance between pro and anti-inflammatory parts of the immune response, and which, in fact, this anti-inflammatory part, of course, is very important because it controls this inflammation. At some point, the inflammation, well, as you say, there are different questions. First of all, the inflammation should not be very strong, because if the inflammation is very strong, so what it can produce what is called inflammatory cell death. This is very bad. So in fact, in your diagram, this uninfected cells, so this inflammation, you explain that as a part of the immune response, they kill infected cells. But if inflammation is too strong, it begins to kill uninfected cells. They begin to kill healthy tissue. This is called inflammatory cell death. And this is, of course, very dangerous. This is in particular also related to what is called cytokine storm. So because killing uninfected cells, they produce even much more inflammatory cytokines. This inflammatory cell death becomes even stronger. And this self-amplifying inflammation can strongly damage the body and even can lead to the death of patient's death. And in particular, during this COVID-19 pandemic, this cytokine storm was largely discussed, and it was one of the, not the only, but one of the main mortality causes during this COVID-19 disease. So, this anti-inflammatory part of the immune response, macrophages and cytokines in particular, but also T lymphocytes, for example, and regulatory T lymphocytes, they control the progression of inflammation, but so that it should not be too strong. But another question is also, it's what is called a resolution of inflammation. So at some point, inflammation should be stopped. And how to stop it? This is indeed a very complex question. And this is what we try to understand with Wissam. Well, there is some moderate progress in this question, but we do not yet completely understand this resolution of inflammation. Of course, we will not discuss it now, but it's a complex question. And of course, these anti-inflammatory macrophages and cytokines are important in this case. Another question related to inflammation, which is also, of course, very important, and we discussed it a little bit, but not too much, and I'd like you to comment also on that about chronic inflammation, because what you talk about now, this is acute inflammation as a normal part of the immune response. So what can you say about chronic inflammation?
I cannot say very much about chronic inflammation. As I remember, they include different cytokines and some interactions also may be altered, but I could not say much about the chronic inflammation.
Right. So yes, indeed, some we don't know yet sufficiently well this what happens.
One moment.
Yes, please.
I didn't understand well. There are different discussion in literature. What is the nature of chronic inflammation? Does it the different kind of inflammation, or does it the prolongation of the acute inflammation, and can be chronic and acute at the same time? As I saw, I didn't find the precise answer to this. Maybe.
Well, so yes, of course, this question should be studied in more detail. as far as I or we understand now, and I think that you found this paper, that some of cytokines or cells are the same in acute and chronic inflammation, and some of them are different. So this is of course very important, because chronic inflammation, it's not only that normal acute inflammation is, for example, longer in time than it should be, but in addition to that, there are some other cells or other molecules which participate in this chronic inflammation. And for example, I have read some papers about cancer, how chronic inflammation acts in cancer. So its role is indeed very important, because acute inflammation tries to stop tumor growth, but chronic inflammation, on one hand, it promotes tumor growth, and on the other hand, it acts against acute inflammation. So all the cells, like T cells, for example, which participate in the normal immune response, so this chronic inflammation downregulates this normal immune response. So it acts in two ways. It promotes directly tumor cells to proliferate more actively, but also it acts against normal immune response. So this is, of course, very schematically how it happens in tumor growth. But what about infection? This I don't know. So what can be the role of chronic inflammation in viral infection? So this I think also an interesting and important question. So of course we know that you don't have it in your scheme, but of course various type of lymphocytes, in particular T lymphocytes, also T1 lymphocytes. In fact, there are too many of different types of these lymphocytes. Also regulatory T lymphocytes and other. So it is possible that somehow this chronic inflammation acts on all these different elements of the immune response, and can maybe, but this I don't know. This is what we need to check. It may be also chronic inflammation can even promote viral infections. This is what we don't know, and I think this is an important question. All right, after this short but I think interesting discussion, other questions from the audience? Well, I don't see other questions. So thank you again for this presentation. We finish our today's seminar. Have a good day. Goodbye.
Thank you very much. Goodbye.
Thank you. Goodbye.